we are going to talk about how to use Excel solver to solve for LP models. The same Excel solver is also available in Lotus 123 and Quattro Pro. Actually, there are other more powerful commercial packages like Cplex, Lindo, Grobis, and so on, which we can also use to solve for mathematical programming models, of course, including linear programming. But because Excel solver is free and also including as an add-on in Excel, we can easily call it if we have data in Excel already to solve the LP models. Please let us use case 2.2 to demonstrate how to use Excel solver to solve for the LP models. In case 2.2, we assume a company called ABC which produce 2 lines of the heavy equipment. ABC produce both the earth-moving equipment line E9 or the factory's equipment line F9. According to the historical data, ABC will make a profit of 5,000 on each E9 and 4,000 for each F9. In order to produce those 2 equipment, we need both Department A and Department B in terms of the machine operations. Department A have 150 labor hours and Department B have 160 hours of available time. Each E9 uses 10 hours of machine in Department A and 20 hours of machine in Department B. F9 use 15 hours in Department A and 10 hours in Department B. We can also summarize the data in the relation table. In this case, we have Department A and B. We have the products of E9 and F9. And we know that each E9 needs 10 hours of Department A, 20 hours of Department B. Each F9 needs 15 hours of Department A, 10 hours of Department B. And Department A have 150 available hours, and Department B have 160 available hours. We also note that E9 give us 5,000 marginal profit, F9 give us 4,000. So that we can have an LP model like this, we are going to maximize the total profit equal to 5,000 E plus 4,000 F. Subject to 2 constraints, 10E plus 15F less or equal 150, 20E plus 10F less or equal 160. Of course, we also have the non-negative constraints for E and F larger or equal 0. As we have learned in graph approach, we can use the graph to solve for 2 decision variables LP models. In this case, we can have E as the horizontal axis, F as the vertical axis, so we can plot the feasible area for those 2 departments. So we can solve for the optimal solution of E equal to 4.5 and F equal to 7. After we plug in the optimal solution into the objective function, we get the optimal value of the objective function equal to 50,500. Because this is a 2 decision variable LP model, we can still use a graph approach. But what if we have 3 products? For example, suppose we have a new technology enabling us to produce a new product called new E9. We can also call it H. The marginal profit for this new E-line will be 7,000. Each new E-line will use 16 hours of machine in Department A and 25 hours of Department B machine. Again, we have this relation table for the 3 products. We have Department A and B, and we have products E9, F9, or new E9. We can use a notation H to stand for them, so that we can have an LP model of this. The company is going to maximize the total profit equal to 5,000 E plus 4,000 F plus 7,000 H. Subject to constraints, 10E plus 15F plus 16H less or equal 150. The second constraint is 20E plus 10F plus 25H less or equal 160. We also have three non-negative constraints. E, F, and H will be larger or equal 0. Right now we have three decision variables so that we can no longer use the two-dimensional graph to plot the feasible area and finally solve for the optimal solution. So that it's too difficult for us to use the graph approach. We have to utilize a solver to. Now, I'm going to demonstrate how to use Excel solver to solve for these three decision variables LP model. I will display the LP model over here on the right-hand side. And in order to call the Excel solver, we must prepare the Excel form at first. At first, we need to reserve some cells for the decision variables. In this case, we have decision variable E, F, and H. But in order to call these decision variables, we must leave some empty cells over here for hold the values for the decision variables. We can highlight these cells in different color. We can put them in red or blue or red in whatever color you want. Right below these decision variable cells, we are going to put the parameters values for these three decision variables. In this case, we have 5,000 for E, 4,000 for F, and we have 7,000 for H. We know that this problem is subject to some constraints. We have department A constraint, department B constraints. Similarly, we put the parameters 10, 15, 16 for the department A, and 20, 10, 25 for department B. They are corresponding to the parameters for decision variables E, F, and H. We can also put the non-negative constraint over here, but actually they are not required. I'm going to show you in the Excel solver later. After we plug in all these parameters, we need to prepare the right-hand side value for the constraint as well. For department A, we have 150. Department B, we have 160. Right-hand side for those non-negative constraints will be 0. And to remind us that this constraint has a sign less or equal, so we put less or equal for department A, less or equal for department B, and we have put large or equal for all those non-negative constraints. So far, we have halfway done to have prepared the Excel form for the solver, but we need to put in some equation in order for solver to call for the optimal solution. Right now, we need to put the equation for the objective function. Although we have the parameters in place, but the solver have no idea about what we are talking about right now. So we try to specify what the objective function look like. So in this case, we have one function called sum product. In this case, it look like it will sum product parenthesis C5 to E5 from here to here. And we have comma, and we have C4 to E4, and that will be those parameters. We fix the location of C4 to E4, and actually they are, in order to call Excel solver to solve for the LP model, we must specify the functions for the objective function and those left-hand side equations. Right now, let's look at the objective function. In the objective function, we can call one function called sum product. But let me explain at first why we want to call a sum product function. As we know, in the linear programming model, we have objective function equation equal to 5,000 times E plus 4,000 plus F plus 7,000 times H. And definitely we can keep going if we have more decision variables. But the problem is when we have 100 decision variables or even more, it's very difficult for us to make a mistake if we're doing this. And it's also very time consuming. So actually, there's an easy function embedded in Excel we call sum products, which will simplify our entire input over here. So inside the sum product function, we have two parameters. The first one will be the parameters for the objective function from C5 to E5, and actually those are 5,000, 4,000, and 7,000. The second parameter will be the C4 to E4, and that will be the empty shell right now hold for those distinct variables E, F, and H. Because we are going to hold the distinct variables in place without change, we add $sign in front of C and $sign in front of 4, $sign in front of E and $sign in front of 4, so that we fix the location of the distinct variable. And then we have the distinct variable shell. Right now, let me try to redo this shell for you, and we can do that from the very beginning. I also remove all the left-hand side equation. Again, the objective function will be equal to sum product parenthesis, and we just drag our mouse to select all those parameters of distinct variables and put comma, and then we select all those distinct variable cells. Because we don't want distinct variable cell to change, we add $sign in front of them, and that's it. After this, we are going to have the same equation for all those parameters. Definitely, we can do it one by one for each resources as well, but it's time consuming. Excel gives us a function to copy and paste to the resources of Department A. If you click on Department A right now, you see that we have the same equation copy from the objective function. The distinct variable cell has been fixed. The only thing has been changed will be the parameters for Department A. And the parameter automatically changes to C9 to E9. And that's very nice. We can keep doing that and just copy and paste to every resources we have. This we just fill this equation to the rest of them. You can also copy and paste to the rest of them. And if you click on the second one, you have the sum product, and the parameter automatically changes to C10 and E10, and so on. If you look at the last one, it's the similar equation, except the parameter change. Now we have prepared the entire Excel file for the Excel solver. So we are going to call the Excel solver. We need to go to the data, and we go to the solver, and we have a pop-out that's for solver parameters. The first part, we are going to select the objective, and that the share of F5 will be our objective. Our objective is to maximize, so we pick maximize over here. We select all those distinct variables in the changing variable cells, and that will be these three cells from C4 to E4. And now we are going to add the constraints. We have several approaches to add constraint. The first approach, we can add constraint one by one, but actually the Excel solver enables us to select all those constraints with the same size. For example, right now we have Department A and Department B, both have less or equal size. So we are going to select the F9 and F10 at the same time. We want to have less or equal the right-hand side value of those two constraints. And we say OK. We can also add those non-negative constraints over here. But because the Excel solver enables us to have a box called make unconstrained variable non-negative, so we just need to click on this without having to adding all those non-negative constraints one by one. After that, we just need to make sure we select the simplest LP because this is an LP model. And then we are ready to solve the problem. We just click solve. In this pop-out, we don't need to do anything for now except to click OK. And we can see the optimal solution already pop out in the distinct variable cells. In this optimal solution, we know that we are going to produce 5.5 for F and 4.1 for H. our optimal value for the objective function is 51,441. We also have those left-hand side equations. If the left-hand side equation value equal to the right-hand side, that constraint is binding. So based on that, we know that we have two binding constraints. Of course, we also have binding non-negative constraints, but the department A and department B will be our focus right now. Thank you.